This video is on exponential functions, and before you start, make sure that you have your graphing calculator available because we are going to be using it quite a bit in this video. So let's look at the top where we're going to define an exponential function. It says an exponential function is the function of the form f of x equals a to the x, okay, where x is the exponent and a is a positive real number greater than 0 and not equal to 1. Now we're going to talk about these two parameters or defining pieces of a. The domain of f is the set of all real numbers. Now why must a be greater than 0? So we are imagining some a raised to the x power, and here is why it must be greater than 0. If a was negative, there would be values for a that would be undefined. For example, if a was less than 0 and you had a to the 1/2, that means the square root of a. But if a was negative, for example, -2, then that would be the square root of -2, which we know we can't do in the real number system. Why must a not equal 1? Because if you had a equal to 1, so if a was equal to 1, you would have 1 to any power, and it's just going to be equal to 1, because so it doesn't matter. So those two restrictions are on that definition of our exponential function, that a has to be positive, so greater than 0, and not equal to 1. There's a star here, and I want to point this out. It's important to distinguish between a power function, which is x to some exponent, where x is the base, and an exponential function where you have a raised to the x. In a power function, the base is a variable and the exponent is a constant. In an exponential function, the base is a constant and the exponent is a variable. So they are sort of just opposite of each other, although they aren't opposite in the way they work. So let's take a look at example 1, where we're going to explore some things about exponential functions. We're going to start by sketching the exponential function f of x equals 2 to the x. So if you would, I'm going to pull my graphing calculator over here, and we're going to go into, let's get out of that. We're going to go into y equals, and I need to clear, and we are going to put in 2 raised to the x power. Now my window, let's set our window. Let's go in and together set the window. Let's set it -4 as x min and +4 as x max. The scale at 1. I don't know what yours is, but yours may be something close to this. Mine was for something different, so it was very, very different. Y min at -1, Y max at 1, 2, 3, 4, 5, 6. So I'm just using this sketch here. And Y scale, we're going to count by ones. Let's hit graph now and take a look at the sketch, the graph of y equals 2 to the x. And I'm going to move my graphing calculator and I'm going to replicate that right here. So it's coming along, it goes through this point, and it looks something like that. This is the function 2 to the x. Now, it says on the same coordinate grid, graph g of x equals 3 to the x, h of x equals 4 to the x, and k of x equals 6 to the x. How are they alike and how are they different? We're going to do that in just a minute, but what I want to do is complete this column, and we're going to do that from your graphing calculator. So what we want to go to, I'm going to bring it back over, covering up the graph, because you can see it both now on the screen and on your paper. And we want to go into second table. This is going to show the x and y values, and let me see if I can lighten this just a little bit. A little bit too much there. I don't know, I was trying to make you be able to see it better, but it's a little bit difficult. So what we want to look at is when x is -1. So if I come down here, there x is -1, then that means that f of x is 0.5 or 1/2. We're going to show it as a fraction. If x is 0, that would be 2 to the 0. Anything to the 0 we know is 1. And again, following down on the graphing calculator, I'm going to try to point here and see if you can see it. X is 0, y is 1. Then we're going to go to x is 1. That makes 2 to the first power, so it's 2. When x is 2, y is 4. When x is 3, y is 8. And when x is 4, y is 16. You can read those right off the table. All right, now we're going to come back to this later, but I just wanted to capture that for now. So let's go back to our graph, and now it says to enter g of x equals 3 to the x. So we're going to leave this one on here. Let me scoot it over. Going to go back into y equals, we're going to keep our y sub 1, go down to y sub 2, and this time we're going to put 3 to the x power. Now I want you to watch where it comes up in relation to our first graph. So here we go. It's starting. Notice where it is. I'm going to use a different color to show you on my sketch. It actually started, it's hard to see where it started down here. It crossed at the same point, and then it came up like this. So this was 3 to the x. All right. With that graph on, let's go into second table, which is second graph. And now let's look at what we're going to be looking at is when x is equal to, and then what y is, so y2. So we're going to start again at -1, and we have 1/3. We go down at 0, it's 1. At 1, it's 3. At 2, it's 9. At 3, it's 27. And when x is 4, we have 3 to the 4th, which is 81. So everybody, I hope you see what I'm doing. All right, let's go now to the next one. I'll try to do this in green so you can see that. And we're going to enter 4 to the x. So go to your y equals, leave your first 2, come down to the next one, 4 raised to the x power, hit graph, watch where it's going to be. There it is. It's inside. It starts kind of below, it crosses right here, and then it's right here inside. I exaggerated mine a little bit. My 2 should have been a little further over this way, 2 to the x, but you can see it on your graphing calculator. This is 4 to the x. And we're going to capture the table for that. So second table, now we're looking at y3. So I'm going to get down to x equals -1. We're going to go over to y3. And y3 is 1/4. So 4 to the -1 is 1/4. 4 to the 0 is 1. 4 to the 1 is 4. 4 squared is 16. Then we have 64 and 256. All right, last one that we're going to do, y4 equals 6 to the x. So 6 raised to the x power. Enter, hit graph, watch again where it comes up. Just inside that 4. So it's down here, it comes up, and it's just inside 6 to the x, like that. There's actually a bigger space here than I indicated on mine. My sketch isn't very accurate, but you can see the accurate sketch right there on that graph. This is the 2 to the x, and then the 3 to the x, 4 to the x, and 6 to the x. Going to our table for y4 and scrolling across to y4, coming down to when x is -1. And now I need to see, whoops, I went back too far. We have y to the 4th is 1/6, because think about it, it would be 6 to the -1, which is 1/6. This is going to be 6 to the 0, which is 1. This is going to be 6 to the 1, which is 6. This is going to be 6 squared, which is 36. Then we have 6 cubed, 216, and 6 to the 4th, 1296. I'm just reading them right off of my calculator. Now, it says, how are the functions alike and how are they different? Well, definitely they're alike in that they all have the same general shape. They also, if you notice, all pass through this point, the point 0, 1, because think about it. Any number raised to the 0 is going to be 1. So that makes sense. It makes total sense. They're different in that they get steeper as the base gets larger. All right, we're going to do this again, but rather than using numbers that are greater than 1, we're going to use numbers, we're going to use 1/2 actually, or numbers between 0 and 1, raised to a power. So we first want to graph 1/2 to the x. So we're going to go into our y equals, we scoot this over so we can see this graph. I think our window is still okay down here, and I'm going to clear all of these out. We're going to kind of start over. Now, we're going to go back to the old one, 2 to the x, because I want you to compare that. And now I want you to type in 1/2 to the x. And you can do that by putting 0.5 to the x or parentheses 1 divided by 2, 1/2 raised to the x power. Now let's look at the difference in these two. We already know that 2 to the x looks like this black line. So let's see how 1/2 to the x compares to that. So here's 2 to the x. You're familiar with that. Now watch the other one. 1/2 to the x is a reflection across that y-axis. So I'm going to draw 2 to the x. It looks like this. But in blue, I'm going to do 1/2 to the x, and it looks like this. And if I could draw nicely, and I did pretty good, those would be symmetric to each other across that y-axis. So now let's fill in. We'll go to our table, second table, and we're going to fill in here when x is -3, what is y? But I think the one we want is our y2. So let's go up one. Oops, it didn't do -3 because I must not have had my window correct. Let's go to the window. I do. I have -4. So I should be able to see x is negative. Yeah, there we go. X is -3. Y is 8. X is -2. Y, if you look right here, x is -2. Y is 4. X is -1. Y is 2. X is 0. It's 1 again, so it still goes through that point, 0, 1. That's that point 0, 1, because anything to the 0 power will be 1. Then x is +1. We have 1/2. X is +2. We have 1/4, and then 1/8. And if you plotted those points, the blue line will show that those points are all on my graph. -3, 8, -2, 4, etc. So that's an exponential function. When your function is greater than 1, it's going to look like the black line. When it's between 0 and 1, and remember, it can't be 1, we said that up here, and it has to be greater than 0. So when it's fractions greater than 0 but less than 1, it looks like the blue line there. So that was a little exploration. If you will take a look at the next page, I did a little summary here. It says graphs of exponential functions are classified into 2 groups depending on the base. So if a is greater than 1, meaning 2, 3, whatever, 1.5, whatever, it's going to go through this point, 0, 1, and it's going to look like this. This is the point 0, 1. If, however, we are talking about a base that's between 0 and 1, it still goes through this point, but it goes the other direction. It's reflected across that y-axis. So the next example says to determine whether the given function is linear or exponential. So to determine if a function is linear or exponential, we have to check two things. We're going to check first the slopes, and I will show you what I mean in just a second. And second, we're going to check the ratios, and I'm going to put in parentheses, of the y's, and I will explain that also. So let's look at this example A, and let me show you what I mean. If I want to check first the slopes between any 2 points, and I'm just going to go down the line checking the slopes. So I'm first going to use these two sets of points, -1, 5, and 0, 2. So my x1, y1, x2, y2, and in fact we should probably label those. And we know that slope is equal to x2, y2 minus y1 over x2 minus x1. Or we have -3 over +1. Which is -3. Now we're going to check the slope now between here and here. So we're checking it again. So I'm using 0, 2, and 1, -1. So x1, y1, x2, y2. That's going to give me -1 minus 2 over 1 minus 0, or -3 again over 1. The slopes are the same. So the same slopes between different points, and I could check any points. I could check between these two. I could check between this one and this one if I wanted. It's always going to be -3. If they all are the same slopes mean this is linear. Now, we are still going to check the ratios, and by ratios I mean the ratio of the y's. So 5 to 2, that's a ratio. Now I'm going to check 2 to -1. And then -1 to -4, those ratios aren't the same. This one is 2.5, this is -2, this is +4. They're not the same. So the ratios are not the same, meaning they are not exponential. This is not an example of an exponential. Let's look at this other one. I think you'll see it better when you see a second one. Again, let's check the slopes on this one. So between these 2 points, I've got -1, 32 and 0, 16. So x1, y1, x2, y2. Slope is equal to 16 minus 32 over 0 minus 1, or -16 over -1, which is 16. Let's see if the next one is the same. Between the points 0, 16, so I have to check 2 sets with slope, and 1, 8, I have that slope would be 8 minus 16 over 1 minus 0. This is -8 over 1, which is -16. So, -8. Those are not the same. So that tells me it is not linear. So how can we show whether it's exponential if the ratios of the y's are the same? So is 32 to 16 the same as 16 to 8, the same as 8 to 4, the same as 4 to 2? It is. The ratios here are all 2 to 1. That tells me when the ratios of the y's are the same is that it's exponential. So when they have the same slopes, it is linear. When they have the same ratios, it is exponential. All right, let's look at the next page using some things that we've done in the past, mainly transformations, and we're only going to do one of these because they're very difficult. It's very difficult to see transformations with exponential functions because they're so slightly different sometimes. So it says graph f of x equals 2 to the x minus 3. Actually, I think it's 2 to the negative x minus 3. Using transformations, determine the domain range and the horizontal asymptote, which we'll talk about in a second. So the parent function is 2 to the x. So we need some points. We know it goes through the point 0, 1. It also goes through the point 1, 2 to the 1 would be 2. If x is -1, 2 to the -1, it's 1/2. And we can continue, but that's enough to get us the graph. So it goes through the point 1, 2. It goes through the point -1, 1/2. And so we know that it looks like this, that parent function. So the first thing that we're going to do is we are going to replace x with -x. And what that does is it reflects across the y-axis. So this is going to turn around across that y-axis. So what happens to our points, I still have the point 0, 1, but now instead of having 1, 2, I'm replacing x with -x. I have -1, 2. And instead of having -1, 1/2, I have the point 1, 1/2. So I still have 0, 1. I have the point -1, 2, and 1, 1/2. So it's going this direction. All right, that was the reflection across, and that was right there when the x was replaced with a -x. It's very tiny, it's hard to see it. Finally, we're going to take this last graph and we're going to do a vertical shift down 3. That's what that means. So that affects, let's write what it affects. That affects the y. This one affected the x. X became -x. So in my point 0, 1, if it's shifted down 3, it becomes 0, -2. So it was 1, down 1, 2, 3. So it's down to here. -1, 2, it's going to go down 3. It's going to become -1, -1. 2 take away 3. And then 1, 1/2, going down 3 is going to be 1, -2.5. So I have the point 0, -2. It's still going to be shaped like this. I have -1, -1. And then I have 1, -2.5. So it's down here, not quite to 3. And it's shaped like this. It went down 1, 2, 3 from what it was there. Now let's talk a minute before domain and range. Let's talk about the asymptote. A horizontal asymptote, and let me use something that will show up nicely on here, is a line that a graph approaches but doesn't touch. So here, this is our horizontal asymptote. The horizontal asymptote here is the x-axis, or y equals 0. Here it's the same thing, but here the asymptote, the line that it never touches, is y equals -3. The domain, left to right, is -infinity to infinity. But the range of my final graph, the lowest it can be is -3, and it cannot include that. And that's my x to infinity. The natural exponential function is the exponential function f of x equals e to the x. And it's something that occurs with such frequency in applications and in nature that it's just usually referred to as the exponential function. E is a number kind of like pi. It's a number that comes up all the time in relationships, in applications, and in nature. So what we're going to do is, again with our graphing calculator, we're going to graph y equals e to the x, 2 to the x, and 3 to the x. And we're going to look at this on our calculator. So let's go ahead, turn your calculator on, go back in. I want you to hit clear for whatever is in there. Whoops, I didn't clear that one. And let's go up and let's first enter e to the x. Now, if you're looking for where e is, if you find your 4 and you look just diagonally and above, you will see e to the x. So we're going to go y equals second e to the x. We're going to put our x in there, hit enter. Now we're going to do 2 to the x like we did before, hit enter. And then I think the last one it said, yes, was 3 to the x. 3 to the x. Now let's remember the order that we did it. The e comes first when we get ready to graph. So I'm going to change my window. 1, 2, 3, 4, 5, 6, 7, 8. So let's go to window. We'll leave our x the same, but let's come down and change our y min is -1, but our y max is 8. Now let's take a look at that graph. Here's the e. Here is the 2 to the x. Look where it is. It's on the right side of the e. Here is the 3 to the x. It's just past the e. So if I capture that, it goes through here. Here is the e to the x. When I did 2 to the x, it was underneath, it was here, and it was over there. That's 2 to the x. This is e to the x. But then when I did 3 to the x, it was super close to that e. This is 3 to the x. What does that tell me about the value of e? E to the x is between 2 to the x and 3 to the x, but it's closer to 3 to the x. So e must be closer to 3 than 2. And if you want to know what e actually is, go back into your calculator, type in second e to the and put 1. And you are going to see that e is 2.718, etc., etc. So e is actually 2.718, blah, blah, blah. It keeps going. So you can see that, yes, it is closer to 3 than 2, and you can see it from your graph there on your page. Looking at the next page, we're going to do an application problem involving e to the x, that exponential function. So it says between 9 p.m. and 10 p.m., cars arrive at Burger King's drive-thru at the rate of 12 cars per hour, which is 0.2 car per minute, or 0.2 of a car. The following formula from statistics can be used to determine the probability that a car will arrive within t minutes of 9 p.m. So if t was 5, it'd be, what's the probability that a car will arrive between 9 and 9:05? If t was 15, between 9 and 9:15, etc. And this is the formula right here. So it says determine the probability that a car will arrive within 5 minutes of 9 p.m. That is before 9:05. So that means that t is equal to 5. So what we are really wanting is we're going to replace that t with a 5 and that t with a 5. So if f of t is equal to 1 minus e to the negative 0.2t, we want f of 5 minutes. 1 minus e to the negative 0.2 times 5. Or if you want to put that in your calculator, it's going to be 1 minus e multiply 0.2 times 5, and you're going to get negative 1. So let's put that in the calculator. We put in 1 minus second e to the negative 1. Don't use minus 1 here. Use negative 1. Oops, I need to show you that. Use negative 1. This here, right here. Not take away when you're doing that exponent. This is for negative numbers. This is for subtraction. We hit enter and we get 0.63212, and it keeps going. 0.63212. What does that mean? It means that there is a 63%, if I change that to a percent by moving it 2 places, chance of a car coming through the drive-thru between 9 and 9:05 within 5 minutes of the start time. That's all we're doing. Now it says determine the probability that a car will arrive within 30 minutes. Well, I would think it would be higher. So this is where our t is 30. So that would mean we are looking for f of 30, which will be 1 minus e to the negative 0.2 times 30. You can put that into your calculator. Go ahead and put that in. If you want to multiply this first, you can, and you're going to get 6. E to the negative 6. In fact, let's do that. F of 30 equals 1 minus e to the negative 6. And when you do that, you're going to get approximately 0.9975 or a 99.8% chance. So the more time that goes by, of course, the greater chance there is of a car going through. Doesn't that make sense? It says, what value does f approach as t becomes unbounded, meaning bigger and bigger and bigger? It approaches, it's never going to really reach, but it approaches 100% chance. Now, if we want to graph this, we're going to put our minutes or our time down here, and we would say 0, let's go 10, 20, 30, 10, 20, 30. I'll show you how to put this in the calculator in just a second. And then we're going to go from 0 to 100%. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100 on the side. And what we want to do is set our window. So let's first set our window and then we'll put in our function. We want x to be the x min 0 to 30 for the minutes. We will count by tens instead of ones. And then our y min is going to be 0. Our y max will be 1, which is 100%. Okay, and we're going to count by 0.1. If that bothers you, you can put in y max is 100 and you can count by 10. It's going to be the same thing. All right. Now let's go in and put in our function so our calculator knows what to graph. Clear out what you have, and the function is what you were given in this problem. So it's 1 minus e, there's my e, to the negative 0.2, we're going to use x instead of t. Hit graph. And you can see what that graph looks like. It increases and approaches 100%. It never quite reaches 100%. There's never going to be 100% certainty that a car will go through. Some fluky thing could happen. So this is our horizontal asymptote right here. But this is what the graph looks like. It approaches 100% as time moves on.